All right, so we are going to continue thinking about the types of transformations that we can make to parent functions. And here we want to consider the quartic function p of x given by x plus 2 to the fourth power. And we want to state the transformations that were used to create p from the parent function f of x equals x to the fourth. We want to show this transformation graphically and decide whether p of x is an even function. All right, a lot going on there. If we break it down, the first part is we want to state the transformation that was made to the parent function x to the fourth. Well, it'd probably be really helpful to go ahead and graph x to the fourth so that we can sort of get a visual of it and think about what might be happening when we look at p of x. So if we do that, and I want you to take a minute right now, pause the video, and actually try graphing it yourself. Good. Now, hopefully you did an accurate job of graphing it, and what you'll find is it's an even function, which is helpful because at 0, I plug in 0, I get 0. When I plug in 1, I get 1. When I plug in 2, I get 16. And when I plug in negative 1, I get 1. When I plug in negative 2, I get 16 again. And I see my quartic function looks just like that. And we'll label it, this is x to the fourth. All right. So at this point, I'll make that a little more legible. So at this point, we want to consider, okay, what happened to this function, x to the fourth, so that I could now create p of x, which is x plus 2 to the fourth, which is again going to be a quartic function, right? So the fourth power, but slightly different. There's a little bit of a difference here. And I think the most helpful way to consider a transformation is to consider what happened to one individual point. Because if we know that what happened to one individual point, well, all the other points have to have had the same thing happen to them, because this quartic function will have the same basic shape, so they'll all have to translate it or transform in the same manner. The point that we always care a lot about, probably the most important point when considering any polynomial, is going to be the roots of the function. So let's hone in on this root of our parent function. The root of this parent function, meaning where it intersects the x-axis, it occurs at 0. And we can see this very clearly because if I plug in 0, I'll do it right up here, f of 0 is 0 to the fourth power, which is 0. All right, so I know it occurs, that one real root occurs at 0. Well, where does the root of p of x occur? In other words, what x value will make it equal 0? Will make our value of p of x 0? Well, that boils down to this question. What to the fourth power is 0? 0, right? So I need to find a way to make sure that x plus 2 is 0. And that's no more tricky than solving this equation. X plus 2 equals 0. What will make it 0? Well, if I subtract 2 from both sides, I'm just going to get that x must equal negative 2. And I can see that that's very clear, right? If I plug in negative 2 for x, I'm going to get negative 2 plus 2, which is 0, to the fourth power, which is 0. What does that tell us? I want you to pause the video right now and try it on your own. What do you think that tells us? All right. Hopefully, what you decided was that now the root of our function p of x, well, we know it occurs at negative 2. Right? It intersects the x-axis when x is negative 2. And so think about what changed. What happened from our original function, the parent function, to our new function? Well, it's pretty clear. The root was at 0, and now the root is at negative 2. What type of transformation was that? It was a translation to the left 2 units, which means every point is going to translate to the left 2 units. So we could actually think about, well, the point that was at 1, right, when I was at 1 originally, 1, 1, that moves to the left 2 units. So instead of it occurring at 1, it will occur at negative 1. And the point that was at negative 1, right here, will move to the left 2 units, so it will occur at negative 3. And that makes a lot of sense. Let's consider another reason why that makes sense. Imagine if you plugged in -1 into p of x. Let's do that work right down below. P of -1 is just -1 plus 2 to the fourth, and that's nothing more than 1 to the fourth, which is 1. Similarly, P of -3 is going to be -3 plus 2 to the fourth, which is again going to be -1 to the fourth, which is 1. If I were to plug in -4 or 0, I would get 2 to the fourth power, which is going to be 16. And so I can really accurately show P of x, which is x plus 2 to the fourth. And I can see that every point has translated to the left 2 units. All right? So to state it clearly, the parent function f of x was translated 2 units to the left to create p of x. Excellent. Now, the second part of this question is p of x an even function? Why might we think that? Well, I want you to try and answer this question yourself. Why might we think that p of x is even? The reason you might think p of x is even is because the parent function was even. X to the fourth is an even function, meaning if I plug in a value and I plug in its opposite value, I'm going to get the same output. Well, does this happen with p of x? Maybe we could think of some examples. Let's think about what happens when I plug in -2. If I plug in -2, I get 0. What will happen when I plug in +2? Well, we can see that we're way out in the stratosphere here, because if I plug in 2, I'm going to get 2 plus 2 to the fourth. I'll write that out right here. P of 2 is 2 plus 2 to the fourth, which is 4 to the fourth. What's 4 to the fourth? Well, 4 times 4, 16, times 4 is 64, times 4 is 216. So certainly, if I plug in -2 and I plug in its opposite, +2, I'm not getting the same value. So because that's an example of where the opposite inputs don't give me the same output, this can't be an even function. If I wanted to show this very clearly, remember p of x is x plus 2 all to the fourth, and p of -x is -x plus 2 to the fourth. Now, if you were to multiply this out, you would clearly see that they're different, but if we just think about it really quickly, we can see that these are not equal, right? If I take some value and add it to 2 and take it to the fourth power, it's not going to be the same always as if I take a negative value. That opposite, additive inverse, add 2 to it and take it to the fourth value. And we saw that with -2 and 2. So this should start to build intuition about what a function has to look like in order for it to be an even function. I'll let you think about that. Maybe you can try and prove it yourself.